Conservation of angular momentum. Hello students, today we are going to discuss conservation of angular momentum. As we have already discussed that rotational analog of force is torque and rotational analog of linear momentum is the angular momentum. And change in the angular momentum with respect to time is denoted as torque and also given by I alpha. So we know that in the absence of external torque dl by dt is equals to 0 or angular momentum is conserved. Its analogy can be taken as in translatory motion where in the absence of external force the linear momentum is conserved. So in this case the term I omega expressed as angular momentum will be conserved. So for a body rotating about a fixed axis, in the absence of external torque, considering no friction here, no friction or other resisting forces, the angular momentum is conserved for body which is rotating. Means I omega is equals to constant, the multiplication of moment of inertia of body with respect to rotationary axis and its angular velocity is constant. You can consider an example here. A person sitting on a revolving chair about its axis. Suppose you are sitting on a chair and tell your friend to rotate that chair. As he rotated the chair, the angular speed is changed by stretching your arms horizontally. If you stretch your arms horizontally, your moment of inertia with respect to the rotationary axis of the chair increases. Hence, the angular speed of the rotation of the chair decreases. And if you bring your arms back to closer to your body, in that case, the moment of inertia of your body with respect to the rotating chair is reduced, hence the angular velocity of your body, hence the rotating chair is increased. So in this manner, since the external force is absent, the person who started the rotation of the chair is not applying the continuous force to rotate that chair. He has done this only once and now he is far. No external force or torque is applying here. Only you are stretching your arms or bringing back your arms to closer to your body. And in both of the cases, the angular speed is changed corresponding to moment of inertia. Whereas the product of moment of inertia and angular speed is constant. So this is a good example to understand in the absence of external torque, the angular momentum is conserved for that body. Now let us take the another term, rolling motion. What is rolling motion? You have observed too many times the rolling motion in your life, whether a person is diving into the river or a person working in the circus. They all take advantage of rolling motion. Wheels are generally used to transport any of the thing from one place to another place, and they do the rolling motion. In the rolling motion of a body, suppose let us consider a disc is rolling without sleeping. That means at any instant of time, a point on a disc is in contact with the surface on which it is rolling. So rolling motion is a combination of rotation and translatory motion. Remember that thing. Rolling motion is a combination of rotating and translatory motion. Consider a figure shown here. A disc is rolling without sliding. On the level surface. Point P naught of disc is at rest. The center of mass of disc moves with velocity Vcm. The disc rotates with angular velocity omega, and Vcm is equals to capital R omega, where capital R is radius of disc. The motion of the center of mass of the disc is translatory motion. It will go along the straight line all time as the disc is rotating, and its direction of motion is parallel to the level surface, whereas the P naught point is at rest at any time instant in the contact with the level surface. Now consider the point P2. At point P2, velocity has two components. V2 velocity has two components. One component is along the direction of center of mass, and another component is perpendicular to the direction of motion of the center of mass. So one component of V2, that is horizontal, is equals to Vcm, and other component of V2, that is the vertical velocity component, is equals to Vr equals to small r omega, where small r is the distance of point P2 from point C of center of mass. At point P naught, the linear velocity is just opposite to the translatory velocity Vcm. The velocity of the point P1 at the top of the disk has a magnitude of two types of velocities. One is Vcm and another is r omega, or 2 Vcm. So at point P1 at the top of disk at any time instant, the velocity V1 is equals to Vcm plus r omega, that will be equals to 2 of Vcm. So its velocity will be twice of the velocity of center of mass and is directed along parallel direction to the level surface. And these all conditions are applied to all rolling bodies. That's all for today. We will take the next topic, kinetic energy of rolling motion, in our next turn. Till then, good day.